Good morning, we are Filippo and Lorenzo, two PhD students from the University of Bologna and Parma in Italy, and today we are presenting our latest work, CalibBEV, which is a new framework that allows us to calibrate LiDAR and camera using bird's-eye view representation. In the autonomous driving field, it's vital to exploit heterogeneous sensors to achieve environmental perception. But what do we need to enable perception? First of all, the sensor suite must be calibrated in order to guarantee data consistency, as accurate sensor calibration enables multimodal sensor fusion, which is the foundation of scene understanding and any other downstream perception task. Finally, relying on fixed calibration introduces risk, since the calibration parameters might change due to different external factors. Therefore, a real-time extrinsic calibration pipeline is usually required for a robust autonomous system. Notably, the LiDAR-to-camera calibration task can be framed as image-to-point cloud registration task, which consists in the estimation of the rigid transformation that aligns a LiDAR point cloud with a reference camera. Previous state-of-the-art methods, such as deep I2P, rely on an initial classification task, followed by a ransack-based correspondence matching stage. However, these methods often struggle with matching RGB and point cloud features, as different modalities and architectures do not produce a shared feature space that can be directly used for matching the multimodal features. Newer methods, such as graph I2P, focus on features consistency by introducing a graph correspondence learning, which consists in transforming the RGB image into a virtual point cloud for the subsequent graph-based pattern consistency learning that fuses the LiDAR and the virtual point cloud features together. Other approaches, as ICLM, leverage the transformer architecture to build an implicit correspondence learning by defining a set of correspondence queries that are specialized as 3D and 2D key points, representing the calibration information. In this work, inspired by the object detection literature, we decided to address the problem of image-to-point cloud registration task from a novel perspective, formulating this problem as a bird's-eye view alignment task. We aim to generate two BEV representations of the same scene, one from the sparse LiDAR point cloud and the other from the RGB image. Then we employ a convolutional decoder to implicitly learn the registration parameters from the misaligned feature maps.
Going into details, for the RGB branch we follow simple BEV by lifting the computed RGB features into the 3D grid. Differently, for the LiDAR branch, we simply scatter the misaligned point cloud features into the corresponding 3D space. Then, following the standard practice, we consider the height dimension of the two misaligned bird's-eye views as the channels of the two top views. These are then concatenated together and fed to a CNN-based decoder module, which is trained together with a rotation and translation heads to predict a coarse calibration matrix. We call this step implicit alignment. Then, we extend our approach with an additional module to further boost the registration performance, building a two-step alignment algorithm. For this reason, we employ a two-step training strategy as well. In the first step, we train the implicit alignment alone to predict the coarse calibration matrix as described before. In the second step, we introduce the explicit alignment module, which replicates the same modules as in the implicit alignment. We call this module explicit alignment because, differently from the implicit, the 3D grid gets physically warped by the predicted coarse calibration matrix, providing to the second decoder closer 2D and 3D corresponding features, in order to facilitate the decoder task. When training this module, we keep the implicit alignment frozen. Thanks to our two-step alignment framework, we are able to achieve state-of-the-art performance in both point-based and projection-based standard calibration benchmark, outperforming by a large margin any previous method. Regarding the standard point-based 3 degrees of freedom benchmark, we achieve an half-degree error and less than a 5 cm error both on Kitty and new scenes datasets. While, regarding the 6 degrees of freedom benchmark, we achieve a cumulative error on all the axes of almost 1 degree and 10 centimeters. We conducted further analysis by experimenting the zero-shot generalization ability of our model by training CalibBEV solely on the left camera images and evaluating on the right camera ones. The results are shown in the table on the left, and we do not highlight any significant performance drop, demonstrating the bonded generalization ability. Then on the right, we demonstrate that CalibBEV is extendable to the multi-camera setup, leading to even better registration performance. We also compare the CalibBEV inference time against other methods. We highlight a faster forward process up to 32% compared to CAR I2P, with respect to our full architecture, comprehensive of both implicit and explicit alignment modules. Next, we show some qualitative results. From the leftmost column, we find the miscalibrated input. The calibration results achieve the VP2P match, CAR I2P, and our methods. And finally, on the rightmost column, the ground truth projection. We choose to make this comparison with these methods because they are the ones with publicly available code. Here, we show some calibration results on the new scenes dataset as well. And finally, some qualitative analysis on adverse weather conditions to demonstrate the CalibBEV ability to achieve high-quality results even in challenging scenarios. To wrap things up, CalibBEV is the first framework that frames the image-to-point cloud registration task as a bird's-eye view alignment problem. Leveraging our unique BEV formulation, we propose a two-step alignment algorithm. CalibBEV is easily extendable to multi-camera configuration, leading to better performance. In the end, CalibBEV achieves state-of-the-art performance both on Kitty and new scenes datasets, surpassing preview methods by a significant margin while being faster and more robust. Thank you for your attention. We leave you with this short video showing the CalibBEV calibration results on a sequence from the Kitty test set, by coloring each point with the corresponding RGB value associated with the pixel projection.